Now, under the topic of electromagnetic induction, you will first need to know what we mean by magnetic flux. Okay, what's the definition of magnetic flux? If you recall what you learned in the magnetic field chapter, we told you that magnetic field can be represented visually by lines of force or field lines. Those lines of force are also known as flux lines. Right now, the number of flux lines through any given area is a quantity called magnetic flux. You can think of it as the number of magnetic flux lines you can see in a given area. That is what flux actually is. So you look at the diagram here, you have a certain area here, and then you have a number of flux lines that pass through that area. That is what we mean by your flux. Okay. Now, the spacing between your flux line or the spacing between your field lines is a measure of your field strength, whereby the closer the flux lines are to each other, the stronger your field is. If you have a higher flux density over a particular area, meaning to say the area has more density of lines there, this means that your flux lines are packed into the area, more flux lines are packed into the area, causing them to be closer to each other. As such, you can consider magnetic flux density B as the amount of magnetic flux passing perpendicular per unit area, where B is the number of flux you have divided by area. Now, it's from this equation here that you will be able to define out what is your magnetic flux phi. Your magnetic flux is measured in unit Weber, and from the first equation you have, flux is defined as the product of flux density and your area. So you want to formally define it inside your exam question, you would just say it is the product of magnetic flux density and cross-sectional area perpendicular to your magnetic flux density. Now, this part here is where you need to always include, all right? If you just say it's the product of flux density and area, it's actually not really complete. You have to specifically say it's the product of flux density and area perpendicular to your magnetic flux density, okay? So your magnetic flux is measured in units of Weber. The next statement here is actually defining the unit. 1 Weber is the magnetic flux if a flux density of 1 Tesla exists at right angles to an area of 1 square meter. Because if you look at the equation above here, you want to have 1 Weber, you would need to have 1 Tesla and 1 meter square. Now, magnetic flux is generally magnified if you use a coiled wire. Each turn of the wire actually will have flux passing perpendicular through, so each turn actually contributes to your total flux. So from here, when it comes to a coil of wires, when you want to refer to the flux, you tend to use something called flux linkage. You use a term called flux linkage. For a coil with n turns, flux linkage is the sum of fluxes through the individual turns. In other words, it's actually saying to you the total number of fluxes through all the turns. So right now, if you have 1 turn of your coil, your flux is really just phi equals to BA. But when your coil has n turns, many turns, the flux will be greater by n times. So your flux linkage n phi is equals to nBA. All right. You're basically multiplying the flux that you have in 1 turn with the number of turns that you have. That's why it's n phi here. Okay. So just give me a moment. Okay, back to what we were talking about. Yeah, no worries. Okay. Yeah, back to what we were talking about. If you wanted to calculate out the flux linkage through a coil with n turns, you look at the example diagram below here. This one is just 1 turn of your wire. The flux that you have is actually 4, because you can see 4 magnetic flux lines here acting perpendicular through your area here. So your flux is 4, but your number of turns is 1. In your case, your flux linkage is really just 1 times 4, giving you 4 only. But then you look at the second set of coil, you now have 2 turns here. You have 2 turns of your coil, and each turn has 4 flux passing through it. So now your flux linkage is going to be 2 times 4, giving you 8. And then for the last one, you have 3 turns of your coil, and each turn has 4 flux passing through it. Your flux linkage here is really just going to be 3 times 4 equals to 12. So you'll notice that whatever you're doing here is really just trying to sum out the flux in all the turns. That's why here we normally say your flux linkage is this. It's the sum of the fluxes through the individual turns. Okay,